we were talking about loop fission and loop fusion. That's another transformation that the compilers can do. So right now we're talking about loop fission, and we said that okay, loop fission is something which uh, is to separate the loops into different tasks, smaller tasks, right? So if you want to do something on PJ, all the elements of the array P, right? And you want to further do something more on those elements. What happens in field fission is you are separating them in different loops. That's fission or distribution, right? So each loop is small enough to have a zero overhead that could be replaced by a single instruction. So for that, what we need is some instructions in our hardware that can replace that simply into a single operation, right? For example, if we have to add all the elements of pj by 2, the same elements by 2, for example, if you want to do something like this, right? So maybe there is an instruction in your instruction set architecture ISA which has an instruction like add repeated, something like that, add repeated. So where you are just going to provide where to start and where to end and what to add, and then it's going to do all those addition repeatedly. Now and if you want to multiply, then you maybe have some other instruction like multiply repeated, so it's going to multiply the different elements together. Now what's happening in this one complex instruction is it's working as a whole loop. So this instruction would be decoded once, it would be fetched once, it would be decoded once. So that's the benefit that you are getting. You are fetching this instruction once from the memory, you are decoding it once from the memory, and within that, G?
Sir, presentation is not.
You're not getting the presentation?
Yes, sir.
Yes, sir.
Oh, sorry. Okay, so I have to do that once more. Right, so I thought, yeah. Okay, that's okay. Thank you for, but you should have told me earlier. I was not checking the chat. So was there something over here? Okay, there was something over here in the chat, so I didn't see that. Okay, so let's do that again. Let's do that again. So I'm talking about the second. So before that, what we did was that's the difference in online classes, that you're not synced with the students, and then
no sir, I have opened Wikipedia. I'm getting referred by Wikipedia.
when the students are in front of you, then obviously you know them and you know what they are thinking about. But when so I have that thing in front of me as a screen, but I was not looking at that it's not been shared. Okay, so before that, what you were talking about, and there was a question by Miss Shirina regarding these two, and obviously so that was also not there in the presentation. So I was talking about that this right hand side is better because you are fetching those elements in the same order in which you have stored them, right? So once this element comes into the cache, the other all elements, so this is going to be a miss, but the remaining are going to be hits, and this is because you are fetching in this way. But in this particular element, because of this loop order, you are getting one element from this and another element from this, another element from this. So this order is not going to be beneficial because you are not utilizing those elements which are brought into the cache. Then we come to the other compiler optimizations to reduce miss rate. That second optimization is to transform your program.
It will optimize in row order, not in column order.
Which one? This one here?
No,
it is going to optimize according to the spatial locality. So if the program is storing it in row major order, then this is the better version. if you had implemented that through Fortran, so Fortran is going to store this in a different way. It's going to store that such that this element would be J0 K0, but the next element would be K0 J1, and then K0 K2, and so on. So in that case, this particular program would be better. Okay, so it depends on
Yeah.
how you are going to store them and how you're going to refer to that. And because all of that is done by the compiler, so compiler knows that which of these orders is going to be better because of how it's going to be stored in the memory.
Sir, do you have the complete matrix of both the solutions? So it's for, in order to get better understanding,
Complete method means
complete matrix of both loops.
they are the same. They are accessing the same elements.
Okay.
They are accessing the same elements. What is the confusion over here? What is the confusion that you people are having? So what I'm saying is we have the same matrix. One of them is store. If we had implemented through C, it's going to store it like this. If we implement it through Fortran, it's going to store it like this. So the difference here is the C is going to store these elements first, then these elements. But Fortran is going to store these elements first, then these elements, right? Okay. So
Okay, sir.
if you're going to store that in a row major order like this, okay, then and you want to access that in the same order, because if you want to access this, then the whole block is going to come into the cache. So the remaining elements are already there in the cache, and you want to access the next one which is already there in the cache. That would be a hit. You want to access the next one which is already in the cache. That would be a hit. And so there would be one miss and the remaining would be hit. But in this case, if you want to, if you are storing it in this way, but you are accessing it in this way, that would be a problem, because you are going to bring in one item and you are going to bring in other item into the cache, but you are not accessing them because the next time you are accessing is an item which is not part of the block. It's part of another block. So you are going to bring in another block into the cache. Then the next item you refer is part of another block. So you bring in another block into the cache. So you keep on bringing more blocks into the cache until your cache is full. And when your cache is full, you remove that earliest block that you brought, and then that was the block that was needed here in the later references. So when you really come to that particular element that you need, that's not there in the cache. So that the this one was also missed. The next would also miss. The next would be also the miss. So you're going to have all of these elements as misses, because the time you need them, you don't find them in the cache, right? So this is not going to give you a good. This particular is not this particular implementation is not going to give you a good cache behavior. So what the compilers are going to do when they feel that you have written a program in this way, they are going to interchange the loop and make your program like this. Looking at the cache behavior, the compilers can change the order of the loop. So this is our first optimization, to change the loops, interchange these loops so that you get better cache behavior. Is it okay?
Yes, sir. Now.
Okay. So now we come to transformations. So what the compilers can further do is transform your code in different ways. So if you have written some code where you want to do something on pj is a jth element of array p. Now this is a single dimensional array, but it can be multi-dimensional as well. So it's just an example. It's a single dimensional array. You want to do some task on pj, then you want to do some more task on pj, right? Say for example, you want to load pj with some value, some constant, say some constant. Then you want to add some more things to that constant, right? So now these are two different tasks happening on pj, but pj is referred 3 times. Okay. So the first optimization is loop fission. Now for loop fission, what we do is if there are many items to a particular element, break them in separate loops. So you want to load every element with value C. Then instead of doing that in a big loop, what you do in loop fission is break that into different loops, so that every loop does the work for all the elements. So what is the advantage in this case? The advantage in this case is normally what happens is for this loop fission, you need an architecture which can replace this whole loop as a single instruction. So let's say we have a single instruction like add repeatedly. Let's say we have an instruction like add repeated, and this can repeat many elements. So you just provide your first element like PJ, and you also provide how many elements you want to do that and to add what to that. So if you provide this, then it's going to repeatedly add starting from this PJ point. It's going to automatically change the index J and then add this constant value to it. Okay. And for example, if you have got some other instructions, so these are just hypothetical instructions that I'm making up. So and there are instructions in a complex instruction set computer, a CISC-based computer. There are instructions where one instruction does the task of the whole loop. Like there, if you have read 8086, that's the best example that I can give you, because many people have studied 8086 processor. So 8086 has got instruction which can do string operations on different elements. So if you want to copy the string, actually what you do is you provide how many characters to be copied. So you provide the starting address and you provide from where in that's the memory location that from where in memory you want to start, and then the next thing you provide is how many elements do you want to copy, and that's a single instruction. And if you have written 100 elements, it's going to copy 100 elements into a specified area, and that's one instruction that's going to do it. So if you want to do some task on elements, on different elements, what you do is you break it down into different loops, and each loop is replaced by a single instruction. So when it's replaced by a single instruction, you fetch the instruction once and you then decode the instruction once, and this means you don't have to repeatedly access memory. You just have to do those operations. The other thing is a loop fusion part. In a loop fusion kind of transformation, what happens is if you have got multiple items to multiple alterations or multiple changes to a particular element, you bring them together or merge them together into a single loop. So you can see here what's happening is, since we are doing it on PJ, so what we do is we have brought that together into a single loop, and we are doing it once for PJ. Now obviously you can see here that this is going to be better, because if you have caches with you, then it's going to better access the temporal locality. So if you remember, temporal locality is that the chances of the same item to be referred again, right? So you are referencing it once, then you are referencing it again, and then you are referencing it again. So you are going to write to that item, you are reading it, and then writing it again. Okay, so you're continuously using that item. So in this case, you are separating them into loops. So you are going to do that once in a particular loop, then you are going to do on different items over here, and then you are going to change your loop and do it on different items. But here what you're doing is, for every jth element, you're going to finish that jth element. So once this has come into the cache, once you're going to bring in J0 into the cache, P0, PJ, or I can say P0 into the cache. So if that is in the cache, you're going to do everything related to that in the cache, and then you're going to remove it. Okay, so this is going to give you better cache behavior, because this implementation is utilizing the temporal locality. Okay, so again, this depends on which one is better. It depends on what options do you have and for what application you want to bring, you want to make it. So this this does not have a good cache behavior, but for some DSP applications, if you can replace that single loop into a single instruction, then maybe it's going to save more time, because you don't have to fetch those instructions again and again. Here, what's going to happen is you are going to obviously replace that as different instructions, which are run again and again in a loop, right? So, but in this case, you are doing the same instruction on different elements. So this is replaced by a single, maybe a single instruction. So maybe this is beneficial, but it does not have good cache behavior, but it could save you more time, right? So which one is better depends on what you want to do, and for what application are you planning to. Do you have a cache with you, or do you don't? Do you uh, have main memory only? So in that case, there are different kind of options, and then compiler can do these transformation on itself. So you're going to write a program, and then if the compiler thinks that it's better to break that big for loop into two different loops, then it's going to do that and replace that as a single instruction. Or maybe if you are doing different tasks on different elements, the compiler can merge them together into a big loop and do every task to that particular element in one iteration, and then it's going to do it for the other element, and then it's going to do it for the other element. So the main idea in loop fusion is that you are going to do all those tasks to a single element together. And if you're going to do that together, this means you are utilizing temporal locality, because you're accessing that same item again. So it's still in the cache. So if it's still in the cache and you're referencing it, then this means it's going to be better and it's going to save more time, right? Is this okay? The other optimization that we can do is loop blocking. This blocking or tiling is not, this blocking is not stopping. This blocking means as a block, as a square block or rectangular block, right? Tile, like a tile. So we are talking about loop tiling or loop blocking, which is another optimization the compilers can do. And for that, we need to look at matrix multiplication program. So if you have a 2D array or matrix, and you want to multiply two matrices together, how do you do that? So if you have got two matrices, then what you do is if you want to multiply two matrices, what you do is you take for one of the matrices the elements of the row and multiply it with the elements of the column, and then you get your answer for a single element here. So you all know how the matrix is going to multiply it. So we take one element, multiply it with another element, then add with it the second element and multiply it with another element, and then add with it another element and multiply it with another element. So let's say if you have got 3 to 3 matrices, then there would be 1, 2, 3 multiplications and 2 additions, and then finally you're going to get one answer. And then you're going to repeat that same thing with the other columns, right? So this is how a matrix is going to be multiplied. So all of you are familiar with this. Now, what's happening in this is you are going to obviously store that in one particular order, whether it's row major or column major. And if it's row major, then all the matrices are going to be stored in row major order. Okay. So let's say we have a matrix A and a matrix B and a matrix C. So all A, B, C are stored in row major order. Now, what's happening is that A is referred in a row major order, but B is referred in a column major order. Although all of them are stored in row major orders, but you can see here that a simple loop interchange cannot help you in a matrix multiplication, because the different matrices are accessed in different ways, and all of them are stored in just one way. So if all of them are stored in row major order, then if you want to access them in row major order, it's going to help you here, but it can't help you here, right? Because you have stored that in row major order, but you have to access that in column major order, right? So what to do in such cases? What to do in such cases like matrix multiplication? Okay, for such cases, we have an optimization which is called loop blocking or loop tiling. Right. So the main idea over here is instead of operating on entire rows or columns, what we do is we operate on a block of elements. We operate on a block of elements only, and then we change our block to a different block, right? So I'm going to come to that by some example. The main goal is that once a block is brought into the cache, you work on those elements as much as possible before you throw them out from the cache. Now, you are always going to get better cache behavior when you utilize all those elements which are brought into the cache. Now, the reason why you didn't get better cache behavior in the previous example was you were bringing in element but never using them and then throwing them out, and then you were bringing them again when you wanted them, but again you are not utilizing the other elements of those blocks, and then you want to throw them out, and then you are going to bring them again. So that's not a good cache behavior, because you're bringing something into the cache but you're not utilizing all of that. And you're going to see the same thing here in matrix multiplication, but blocking is going to help that out. So I'm going to go through the matrix multiplication program here. That's the matrix multiplication program. You can go through that yourself as well. So we have two loops here, which are, but before that, let's talk about the matrices. So let's say we have got three matrices, matrix X, Y, and Z. So Y is our matrix which we need to multiply with Z. So Y needs to be multiplied by Z, right? So Y needs to multiply by Z, and the answer has to come in X, right? So this is what we need. Now, obviously, we have just discussed that Y has to be accessed in a row major way, but Z has to be accessed in column major ways. So you are going to get those elements. Now, let's say we have stored them in row major order. That is, all those elements of the row are stored together. And when the fifth element finishes, then we are going to start from the second row, right? So if you want to look at how they are going to be stored in memory, Y would be stored like this, that 0 0 would be there, then 0 1 would be there till you reach 0 5, which is this element, and then you are going to start with 1 0 and then 1 1. So this is your row major order. If you want to see how Z would be stored, again, if you're going to store one of them as row major, everyone would be row major. So everyone is going to be stored like this: 0 0, 0 1 till you reach 0 5, and then it would be 1 0 and so on. So all of them are going to be stored in this way. That is the row major order. So all the rows are going to be stored first. When the row finishes, then the next row, then the next row, then the next row, right? So this is how it's going to be stored in memory, right? This is how it's going to be stored in memory. Now let's look at the matrix multiplication, because we are accessing Y also in row major order, because we are accessing these elements also. So that's going to be okay. But if you're talking about Z, if you need this element, you're going to bring in the whole block, but you are not going to utilize the other elements of that block. So that's not going to give you a good behavior. And this is an example over here that shows you how to multiply these matrices. The main part here is done over here, that what you're doing is multiplying these elements I. So you have taken two matrices, two loops I and J, with indices I and J. So I here is referring to the the row element of the row element over here. So we are talking about 0th row, which is not changing, and j over here is the column element over here. So this is the column over here, right? So you are multiplying this, right? And then you are changing k, which is the element represented as column over here and the row over here. Okay, so the next time you are going to multiply the same thing with this, because k is going to change, right? So you have y 0 0 with um, y with k 0 0. Then you're going to change y 0 1 with k 0 with k 1 0. Then y 0 2 with k 2 0, and so on, right? And then you going to get some results. So you're adding those results together as well. So these are the operations, and then finally you're going to write them back into x, right? So this is a simple matrix multiplication program. I hope it's clear. Now, what's the problem in this program? The problem in this program is that this z matrix is not giving you good behavior. Again, for the same reason that we talked earlier. It's not giving you good behavior because it's stored in row major order, but you're accessing in column major order. Okay. So what to do? And now, first of all, let's talk about how many memory references are there. How many memory references are there? How many times do we have to access an element? So all of these y, z, and x are memory references. How many memory references are there in the program? So let's say all of them are n into n arrays. In our example, we have the value of n as 5, but let's talk about n in general terms. So all of them are n into n matrices. So if you want to multiply two n into n matrices, the result is also going to come into n, right? So how many memory references are there? So every time you access a y, that is considered as a memory reference. So how many times are you accessing these elements? So let's suppose R is an internal register. So let's not include that into the calculation, but we are going to include all those y's and z's and x. So how many are there? Yes, anyone? Okay, how many times are we accessing the yth element? Any element from the matrix Y. How many times are we accessing that? How the yth matrix? Come on.
N cube,
N cube, right? So if this is run n times, and this is run n times, and this is run n times, then you are accessing y n cube times. Okay, that's simple. That's simple because you know in nested loops you repeat the same loop again and again and again. So you multiply all of them. So n cube times, right? Okay, how many times are we accessing z?
Sir, it is also n cube.
It is also n cube, so this means we need to add this as well over here. And how many times are we accessing x?
Sir, n times.
Y n times?
No, sir, n square.
Y n square?
Because n into n, it is outer of the innermost loop.
Okay, so it's not part of this loop. It's not part of this loop. So this is accessed outside this loop. This means it's only going to run n into n square times. So the total references that you're going to have are 2n cube plus n square for any value of n.
Yes.
Right? So these are going to be a total references 2n cube plus n square. Okay? for n cube operations. So if you have n, any value of n, so you are going to have 2n cube plus n square reference. Now let's look at how to improve this. Now, what is the problem with this particular version? What is the problem over here? The problem over here is if this matrix goes high, if this value of n is quite big. Now we have shaded that in different ways. So the dark gray are the recent transactions, the last three recent operations. So what happens is in the last three operations, you're going to see that you are referring to this white row, second row, and these three columns, right? And these three values would be set. So for this one, the whole row is going to be multiplied with the third one. For this one, the whole row would be multiplied by corresponding elements of the fourth column. For this one, the whole row would be multiplied by the corresponding fifth column, right? And if you did for the three more, then you're going to see that these three are going to involve again this row and the whole matrix over here. So you see here that this Z matrix is utilized fully. If you have enough space in your cache and you can hold this whole thing in the cache, then it's okay. Because if you can hold the whole thing in the cache and at least one row of Y and one row of X in the cache, then it's going to be okay for you. But if the value of n increases a lot and you cannot have the whole thing in the cache because it has increased the size of the cache, then this means that even with fully associative cache, you cannot hold those elements. So this means that you're going to bring in part of Z. And if you have got part of Z in the cache, this means that, because this diagram shows here that we need the whole Z matrix to be in the cache to get any benefits, because it's accessed in such a way that you need all those elements. But if you cannot hold them together, if you cannot hold the whole matrix together, then you are going to continuously bring in and replace other blocks, right? So the problem here is if n goes high, this whole matrix has to be in the cache. But if you cannot hold that, this means you are frequently going to replace different blocks. Okay. Now let's look at the tiled version. Now what's going to happen in tiled version is we are not going to do the whole operation of a whole row with a whole column. We are going to actually divide that into tiles or blocks. So we are going to say, let's say 3 into 3 size blocks. Okay, so you can have any size, but let's say 3 into 3 size. So, and for Z as well, 3 into 3 size. Now the idea is that normally what happens is that we are going to bring the whole block and do operations on the whole block, but this time we are going to bring in the whole block but do operations in tiles. Okay, so if you're going to bring this block, and let's say if you're going to bring this word, and let's say along with this word a block of size of 4 element also comes in, that is say this thing comes into the cache. Our block size is 3, which means that block size defined over here is 3. So let me be a little more clear. So we are talking about cache blocks. That's a separate thing. And we are talking about that loop blocks. That's a separate thing. Okay. So cache block, you all know what cache block is. So whenever a word is needed, a whole cache block comes into the cache. Loop block is that we are going to change our program and work on block sizes of those arrays. Not on all the elements of the arrays, but only a block size of that array. So we are going to change a technique to multiply. Now, what's happening here is when you are going to refer to one item, a whole block comes into the cache. So if you're going to refer to this item, this whole block is going to come into the cache, which is consisting of 4 consecutive elements. When you refer to this element, again a block comes into the cache, which is consisting of 4 consecutive elements, right? Now, if there were only 5 elements, then your next block would be something like 4, 5, and 0, 1 of the second row, right? But let's say we have a bigger matrix, so this is continuing, right? So there are more elements in this particular row. Let's think about that in this way. So if you want to refer to this particular element, then you're going to bring a block of 4 elements. If you want to do work on this, then you're going to bring in the block of 4 elements as well. Okay. The same goes over here, that if you want to work on this element, you bring in a block of 4 elements, and so on, right? Now what's happening here is we are working on a one block of 3 into 3. So we are going to start multiplication from this element to this element. This is okay because both of them were not there initially in the cache, but you brought this and you brought the other ones as well. You brought this, you brought the other ones as well. Then you want to multiply the second one with the second element of that second row, first element of the second row of the Z matrix. So you're going to do this multiplication. So this is going to be a hit. So keep the tracks of hits and misses. So the first one is a miss, but second one is a hit because you have found that in the cache, because that has come when you brought in that block. This is again going to be a miss because this is the first element to that first reference to this block. The third time you want to access this is going to be a hit as well because it's already there in the cache. But the third time you want to access this, it's again going to be a miss over here. Okay, is this okay up till now? So we have got just 2 hits because once you brought this one, you brought other elements of that block which are already there in the cache. Now in a normal matrix, what you're going to do is you're going to continue with this third, fourth, and fifth element, right? And you are going to multiply with third, fourth, and fifth element of Z. But in the blocking approach, you're going to change your approach. So you're going to do 3 elements with 3 elements. So 3 elements with 3 elements are not going to give you the whole result, but it's going to give you some partial result. Now, when you're going to multiply 3 elements with 3 elements, this is a partial result because 3 more elements with 3 more elements are still left, but you're not going to work on them yet. Okay, so you're going to do some partial work. So you're going to multiply this with this, and then you're going to get some partial result. So you're going to store this partial result over here. Okay, then what you're going to do is you're going to change your row. Now when you change your row, or you can even do the same thing on the second one, because in the second operation, what you're going to do is you're going to start multiplying this with the second one to get the result of this one here. Then you're going to multiply this with the second one to get the result over here, right? So what you can do is do the same 3 operations with the next column as well. Now, since you have brought this into cache, if you want to do it on the next 3 elements, that is these 3 elements with the next column, then you again going to see that this is also already in the cache, and all of these are also in the cache. So you're going to get hits over here. And if you want to do this, and then you're going to get some partial energy.
Sorry, sir. Sir, I just want to confirm that, sir, you have marked the four element of the block, but you are discussing the 3 element of the block, sir.
Yeah, because this is just because I want to illustrate that these two can be different. A cache block can be different, and the block on which you want to work can be different. It's better if they are same, because you are bringing the whole thing into the cache, so you need to work on the whole block, but they can be different.
Okay.
Right? Do you get this? So if I say the cache block is 4, but I need to work on 3 elements on over here, then this can be this can happen, but it's not going to be efficient. It's going to be efficient if your value of b is also 4, because then you are going to bring in the same blocks and work on the same elements as well. Okay.
Okay, thank you so much.
Okay.
Okay.
Now, you what you see here is what we are not computing the whole results in one go. We are computing them in different versions. So we are talking about doing one row with one column, then doing the again with that row with another column. But since that is already there in the cache, so it doesn't matter how big your n is, because since you are working on a small size, so that particular size can always come into the cache. So you have brought that into the cache and you're fully utilizing that before throwing it out. That's the main idea. So you're going to do 3 computations first, then 3 more, then 3 more. So you are also utilizing these, and that's also going to be a hit the next time. And you're going to get some more results over here. Then you're going to change your row, right? So you're not going to continue with that the same row. Then you're going to change the row of y, and then you're going to come to that same column over here, right? So since this is already in the cache, all of these are now going to be hits. These first references are going to be hits, because when you're going to multiply this with this, and this with this, and this with this to get this element, this is going to be a hit as well. So you see that you are going to utilize all these elements of Z completely. So once you are bringing that into the cache, you are utilizing them fully. Then you can throw it out when it's not needed. So you're going to get some partial results. You're going to get some partial results. They are not full results. Then you can throw this block out and work on another block, right? And so on, third block, and so on, fourth block. And maybe you will need this block again, so you can bring that block again. But whenever you bring that block, you are working on all those elements of that particular block, that particular loop block that you are going to bring in, right? So that's the main thing. So now I'm going to come to that example of blocking. Now this is a change in algorithm. You can go through that yourself. It has got more loops. That's because you are dividing that into different blocks. So you can go through that yourself. The main idea is that you are increasing, in fact, the number of references to the memory. That's not the main thing, because there are many loops now. But the main idea is that the elements that you're working in, you are trying to utilize all those elements that have been brought into the cache before throwing them out. So you have changed your behavior, your program in such a way that these elements, if they are brought into the cache, your program should utilize them fully before throwing them out, right? And so you can go through that yourself to see how it's going to work. Here we have taken the block size as 3 in this example, in this example over here. So you can see the last 3 references, as I've shown here, that this one is now working with this one and this one and this one here, right? So to get the partial elements over here, and then if your block size 3, you're going to work on these 3 and these 3, right? So next time you're going to start with this one and this one to get partial results over here. Then you're going to change your block and come to this block over here. Again, this block has to do its task with the different elements over here. Okay, so that can be done. And then you have got these ones that needs to be working on these ones, this ones on these ones, and these ones on these ones. So that can be done over here, and this is how you're going to change the program. So I just go through that, because we don't have much time in this lecture, but you probably would need more time to just figure it out how it's working. Explanation is also there in the book, so you can go to that. It's quite simple. It's not very difficult. It's just that you have changed how you want to store that. So instead of previous version where you were storing the value of r directly in xij, now you are adding the previous contents, the previous partial results also in the new computed result, and then storing it back, right? So if you want to compute this result here, it's actually this whole row with this whole row, but you are doing 3 elements at one time, and then later on you're going to have the next 3 elements when you bring in this one here to get the full answer, right? Okay, so this is applicable when you don't have all those elements referred in one major order. So if some of them are referred in row major order and the others are column major order, then a blocking approach is going to be beneficial, right? So this was our 8 optimization, that is compiler should change the program to increase the chances that the elements are going to be present in the cache, and this is obviously going to reduce the miss rate. Coming to our 9th optimization, this is actually about hardware prefetching of instruction data, and this is applicable in all the recent processors these days. Now, hardware prefetching of instruction, the word prefetching, as you all know, is to fetch in advance. Hardware prefetching means that you want to do that as part of a hardware. There would be some hardware which is going to prefetch instructions which are not needed, which are not actually needed at that time, or data which is not actually needed at that particular time is going to be prefetched, is going to be fetched in advance in anticipation that you would need that later. Okay, so that's the main idea here, and it's used nearly in all the systems today these days. Okay, so obviously whenever you have it's assuming that you have got some extra bandwidth, because prefetching obviously means you are fetching more from the memory. So the main idea is if you want to bring some instruction, don't bring a single block, bring 2 blocks. So if you have a word, like if we want to fetch one instruction, so say this is our instruction that we need to fetch, and this instruction is part of this block that's going to be moved into the cache. So the whole idea is, instead of fetching one block, fetch 2 blocks together. So one block would be the one which is needed, right? This is the block which is containing that particular word which is needed. So that block is moved into the cache, but the other block is not moved into the cache, rather it's moved into a stream buffer. Because if it's moved into the cache, it is as if you have changed the block size, but it's not going to moving into the block. It's going to moving into another structure, which we are going to call as a stream buffer. So whenever you are going to fetch a block, you are going to bring in 2 blocks. That's prefetching. So this one is what you needed, but this one is a prefetch one. So you are
Excuse
going
me,
to
sir.
G.
Sir, sorry to interrupt you, but from the term hardware, I just got a question. Sir, ये पूछना था कि for example, in the previous optimization, we have seen that we have the row measure approach and the column measure approach. But can't we have the cache with both of the approach?
No, caches don't have a row measure or column measure order. Caches are going to take in block in a sequential way, right? So whatever is there in the memory in contiguous location, that's going to be considered as a block, and that's going to move into the cache. This is the main thing. So in a cache, it's always going to be contiguous locations, blocks of contiguous location coming in together and stored in a single line, right? And obviously they are of contiguous location, that is they are of next location 100, 101, 102, 103 and so on, right? So if you are storing it in this way, and they are going to come in this way in cache as well as a block because a block is of contiguous location. Blocks cannot be of discontinued locations, right? So block is going to be of contiguous locations. So for example, if you have got 8-bit blocks from 100 to 107, they are going to come into, these words are going to come into a single line as a block, right? So if your program is accessing 101 and then later 102 and then later 103, that's beneficial. But if your program is accessing 101 and then later 116 and then later 125 and then later 130, that's not going to be beneficial, because you're going to bring in more blocks into the cache, because all of these words are from different blocks, and these words means you are going to bring in more different blocks into the cache. It's going to fill in the cache quickly. Okay, so that's not going to be a beneficial approach. Okay, but that's a different optimization that we have already talked about earlier while discussing a loop interchange. This here, hardware prefetching means that if you want to bring in block from main memory into cache, so there is one block that you have always been bringing into the cache, and that was the block containing that word. In a hardware prefetching, we are talking about bringing in two blocks, one which is required and the one next to it, right? Why the one next to it is, this is because you are thinking that once the elements over here are going to finish, or you're thinking that whenever you are going to refer to an item over here, the chances are that the next element can be from this block. Okay, so in anticipation that this would be from this block, you're going to bring in this block, but you're not going to store it in the cache, because cache has got space for holding one block at one time. So you're going to store it in a special hardware which we are going to call as a stream buffer, right? So this second block goes into a stream buffer. Now, whenever the CPU is going to generate any reference, it's going to check both of them together, the cache and the stream buffer. And if it finds that element in the stream buffer, then it cancels that cache access and gets that element from the stream buffer, right? Sometimes it happens that this element, if it's referred by the CPU, it is promoted and it's brought into the cache, right? So this is how it works. So this is how it works, that instead of fetching one element, instead of fetching one block, fetch two blocks on a miss. So you talk about fetching two blocks on a miss, the requested block and the next consecutive blocks, right? So the next block is stored in an instruction stream buffer. Sometimes you can have different stream buffers for instruction data. So you can have an instruction stream buffer as well as a data stream buffer, right? So that would be called the data prefetching. So both instruction and data prefetching are there in Core i7, and it's implemented for both level 1 and level 2 caches. And you can stop that, but it's you have to be a little savvy, and you need to change some bits internally to stop the prefetching. Normally it's open. So and sometime in later processors, what happened is that they have they are not just the next block, but they are blocks which are referred next. So even if you have got a random block, it's going to predict that this block is going to be referred next. So it's not what happens is it has, if you're talking about instruction stream buffer, it has both previous instruction stream and the next instruction stream. So it holds or it maintains both of those streams. So whenever that instruction has been referred, what was the previous block that was referred to it, what is the next block going to be that is referred to it, all of that is also stored in different stream buffers. So even though you have got random order, this can be different. This does not need to be consecutive, the next block. So here it's written that the requested block is the next consecutive block, but the later processors have changed that, and the hardware prefetching just learns from your fetching and accessing. So it's going to take some time, but then it learns that if this instruction executed, what is the next instruction that you are fetching, from which block you are fetching. So it's going to store that block in the later, or you can say the next instruction stream buffer, and this is the previous instruction stream buffer. So it maintains two different instruction stream buffer, but that is a little advanced thing, okay. But the main idea is that once you get a block, you fetch more blocks. The simplest thing is you fetch the very next block, the very next sequential block, and this means that it has good chances because of spatial locality that the next reference is going to be go to that particular block, but it's not going to come into the cache. It's going to come into a spatial buffer. So you already talked about that and the other things here. So it's more effective for instruction caches than D caches. That's obvious because instruction caches have got better spatial locality. It's targeting spatial locality, and it's got better spatial locality. Here is a graph showing
Excuse me, sir.
G.
Again, sorry to interrupt you.
No, you don't have
Sir,
to say sorry. It's your job to. You can say it's your task to ask questions.
okay, sir. Thank you so much. Sir, in the previous page where you have written some arrow, can you please go to the sheet, the page sheet where you were drawing some memory and buffer lines? Yes, here. Sir, my question is, can the CPU directly access the stream buffer or not?
Yeah, CPU directly accesses the stream buffer.
So
Whenever
then,
CPU sends a request to cache, it also searches that in the stream buffer. And if it can find that, it cancels the request for the cache and then gets that element from the stream buffer.
sir, couldn't we replace the caches with stream buffer? What is the main difference between the stream buffer and the caches?
Actually, cache is a big storage space, but stream buffer has got just few entries. It can hold a few number of blocks, but cache is a big entry. Cache has got a lot more storage. You're going to frequently refer to that. Stream buffer is holding just the next block, and if you find an element, you can promote it to the cache, which is written over here. That if there is a hit in the stream buffer, you can move that line into the cache, which is sometimes called as promoting. This is again another optimization that you can do. But if it's costly in terms of hardware, then you can also remove that optimization. It's not necessary to move that line into the cache, but it's better. There are chances that you're going to refer to the next element within that particular block. It has got a term as well, right? Like promote. It's called as promote to bring that up. So your question was, what is the difference between that? So cache is a very big structure. It has got a bigger space. It holds different blocks from different elements. It's got a mapping technique and replacement technique. Stream buffer is just holding the next block of that cache here, so that if it's required, then it can be given earlier in time, because once you are fetching, it takes little time to fetch more blocks into from main memory if they are consecutive in location. So the whole idea is, if you are bringing something into main memory, you're going to bring two different elements. So one block goes over here, the other one goes to instruction stream buffer. Okay, so this saves a little time, and it's not occupying the space of the cache, not utilizing the space of the cache. You're holding it in a different space. So if you get some other block, if you want to refer to some other block from main memory, then that particular block is going to go into that stream buffer. So it's going to quickly replace the stream buffer. So stream buffer is not a structure which is properly maintained, but cache has got a structure which is properly maintained, right? So stream buffer is going to frequently change. Whenever you're going to bring in another block, the stream buffer is going to change. Okay, right?
Okay, sir. Thank you so much.
Okay. So this is a graph showing you the speed up when prefetching is on, the hardware prefetching is on. So you can see for all this benchmark program, the spec benchmark program, there are advantages of, there is always an advantage of prefetching. Although prefetching is going to utilize more bandwidth, sometimes it slows down the program because you are prefetching something useless, and if your memory cannot allow that, then you are probably going to waste time there because the memory is going to be bogged down and is going to refer to items which are never used. But prefetching has to be intelligent, and to make that prefetching intelligent, obviously hardware prefetching cannot help you out. So we go to the 10th optimization here, which is the compiler control prefetching. Now, what happens in compiler control prefetching is that you have got instructions for prefetching. So you can write those instructions, or the compiler can write those instructions in your program. So again, in a compiler control prefetching, you are relying on extra bandwidth with your memory. You are relying that the bandwidth of the memory is more. So you start prefetching from any location you want. By the time you are going to actually access that element, it's going to be there in the cache. So if you get that in the cache, this is what you wanted, right? And it's not going to result in penalties. Okay, so the whole idea is that you want to get something which is not in the cache, you have to wait for it. Why wait for it? Bring that in advance because you know you are going to access that, right? So if you can order that in advance, by the time you come to that instruction, if you get that in the cache, that's going to be helpful for you. The time which is wasted in getting that from the cache, that would be actually utilized in doing some useful work. Okay, so that's the whole order. That's the whole idea behind prefetching, compiler control prefetching. So I'm going to give you some examples here. You can go through that yourself, these points that I have mentioned. So if it's still not clear, I'm going to give you an idea of what a compiler control prefetching means. So let's say you want so let's say you are at NAD and you want a box which contains some useful items for you, and without that box you cannot start. So maybe you are making a project here and you need an oscilloscope or maybe some other item which is there someplace far away, right, which is going to take you something like 1 hour to get that item from someplace else, right? So you're going to take some time to get that item from someplace else. So if you want to do your project and you are stuck at that point where you need that item, so you have to wait for 1 hour to get that item. So and once you get that item, then you can start your work, right? Now, before starting that project, if you order that item from someone else, okay, so one thing is that you go and you bring that, and that's going to take 1 hour, and then you can start your project. But if once you are going to start that project and you know that you would be needing that item, so you ask someone else to bring that item, and by that time you go on and continue with your work. And when actually you need that item, and if it's with you, then you have saved that 1 hour. Is this okay? Right? So one scenario is you started a project, you were doing something, it took some hours for you to come to a point where you need another maybe a device that is placed somewhere else, and you have to fetch that thing from somewhere else, and it's going to take a lot of time to fetch that thing. So it's going to take 1 hour, and you did your project, you came to that in 2 hours time, say for example. So for 2 hours you were doing something, and then you completely come to a stop because you needed an item and it's not with you. So what you're going to do is you're going to fetch that item and you're going to bring that as maybe some device or something. It's placed somewhere else. You go there, you bring it back, you waste 1 hour, and then you can continue with your project, right? So how do you optimize this whole scenario? So you know that you would be needing that thing. Okay, so when you were starting that project, if you could have ordered someone to bring it from that place, right? So what is going to happen is by the time you are completing your project, those 2 hours that you were starting, that person is going to bring that device to you, so that when you reach that point when you actually need that device, you don't have to wait, you always have that device with you. So would you be needing this extra 1 hour? Yes.
No, sir.
No, you won't be needing those extra 1 hour because you have already that device with you. The same goes for instructions. So in a program, you have got different accesses, right? And each axis takes some penalty to fetch it from the main memory in terms of cycles, right? So let's say if fetching it from main memory takes 25 cycles, right? So, and from here to say here takes about 25 cycles as well. So what you can do is when you are here, you can order this instruction. Okay? When you are here, you can order this instruction. And when you are here, you can order this instruction. Right? And when you are here, you're going to order this instruction. So what you're doing is you are pre-fetching instructions. Okay? You know that every instruction is going to take something like 25 cycles, but by the time you are going to reach there, it's also going to take you 25 cycles, right? So you start by ordering from your first cycle, but you're not going to order your next cycle, your next instruction. You are going to order something which is quite far away, so that by the time you come over here, you actually have that. So for the first 25 cycles, you're not going to get any benefit, because if there is a miss over here, then it's going to take obviously some time. But once you reach at this point, since all of that has been pre-ordered, you're going to find out that that is already there in the cache. So all of that becomes hit, right? So this is a simple example of a compiler control prefetching. So if you have got enough bandwidth, what you are going to do is you are going to start prefetching according to some particular order, right? So it's not going to be the next instruction, because that happens in hardware prefetching. In a compiler control prefetching, you have instructions and you have your own liberty. You can order from anywhere of the code you want, right? So the compiler is going to start prefetching from some other location in anticipation that by the time you're going to reach that point, that instruction that you had ordered some cycles ago is already there in the cache. So if it's already there in the cache, that is obviously going to benefit you. So we are going to do some simple example over here. See what you got in this discussion. So let's assume we have an 8 kilobyte direct mapped cache with 16 byte blocks. Okay, and it's a write back cache that does write allocate. So just to remind you all, in a write back cache, what happens is we only update the cache, not the main memory at that time. That main memory is updated only when that block is removed from the cache. Okay. And in write allocation, what happens is if you cannot find a word in the cache when there is a write miss, you bring it first into the cache and then you only write it there. So write back cache normally goes with write allocate, right? Because it's better to write it in the cache only. So it's, if you're writing it only in the cache, then it's better to bring it into cache, because the second reference can also be write to that place. You can have write back cache with no write allocate as well, but in this case we are having write back cache with write allocate. Okay. Okay, so this was
Excuse me, sir.
G.
Sir, kindly ये राइट एलोकेट एंड राइट नो राइट एलोकेट का डिफरेंस दोबारा बता दें.
In write allocate, if you don't find a block in the cache, you bring it in the cache. In no write allocate, if you can't find a if you can't find a block in the cache, you don't bring it in the cache. You just write it in the main memory. Okay. You wanted some block. You wanted to write some value. So for example, if I have a variable a is equals to b plus 4, right? So b was in the cache. 4 was an element that I have to add to b. but A is not in the cache. Now this is a right miss. A is not in the cache. Now I've got two options. Because A is not in the cache, one option is bring A in the cache first. So bring A to the cache first and then update A, right? The other option is don't bring A into the cache, just update A in main memory only. Because it's already there in the main memory, don't bring it in the cache, just update it in the main memory. Okay, so if it's not there in the cache, you don't have to bring it in the cache. That's no write allocate. But in write allocate, if it's not there in the cache and you want to write to it, you first bring it in the cache, then you write in the cache only because write back. Okay, right. So
Thank you, sir.
the elements of A and B are 8 bytes long, so it's a double precision number, 8 bytes. Since they are double precision floating point array, there are 3 rows and 100 columns for A. So A is a matrix having 3 rows and 100 columns, and B is a matrix having 101 rows and 3 columns. Okay, so they are quite different shape matrices. A has got 3 rows and 100 columns. So A is something like this. It has got many columns. B has got 101 rows and 3 columns. So B is something like this. Right? So this is A and this is B. So let's also assume they are not in the cache at the start. So let's assume that nothing is there in the cache at the start of the program. Okay, so what we need to do is find the number of data misses. For what? For this particular program. So you can go through this. For I is equals to 0, I less than 3, I plus 1. For j is equals to j less than 100, j plus 1. Aij is equals to bj0 into bj plus 1, 0. Okay. Yes. So you can go through this yourself, try to see what, and try to find out if whether you can find the data misses here, or how many data misses are going to be there. So what's happening over here? Now, in order to find data misses, what we need to do is try to break this statement according to values of I and j. So what we are doing is having a 0 0 the first time. So it's difficult to write the bracket. I'll just write 0 0 next time. Is equals to j value is 0 for the first time, so it would be b0 0 multiply by, because j plus 1, so it would be 1 0. Now we have 8 kilobyte direct map cache with 16 byte blocks. So the block size is 16 bytes and each element is 8 byte. This means how many words can come in a block? Yes? Come on, quick. How many words can come in a block? Come on.
Sir, 2.
Where are other people? Yes, the answer is 2, but where are the people? Fahad Khan, Yasir. Are you getting this? Are you?
Yes, sir, I'm getting.
Okay. Okay, so there are going to be two words per block. So with the picture that I have shown earlier of A and B, because they are going to be stored in row major order. So A has got something like this,
Yes, sir.
this structure, and B has got something like
Excuse me, sir.
G.
सर मेरे पास इलेक्ट्रिसिटी नहीं है तकरीबन 2 आवर्स से माय लैपटॉप इज गोइंग टू बी पावर ऑफ उसका होने वाला है तो जब तक है आई एम
Yeah, this is actually recorded, so you can view the recording later. Okay.
Yes sir, just I wanted to inform you, जब
Okay.
तक charging है तब तक चलेगा, ठीक है
Right, right,
sir?
right. That's okay. That's okay. Okay, so
ठीक
A is something like this. This means that if you want to refer to A elements over here, so a block size is of two elements. So this means if you're going to fetch one element of B, you're going to bring in another element of B as well, right? And if you're going to fetch one element of A, you're going to bring in another element of A as well, right? So next time this would be a hit, right? Okay, so let's see how the program is behaving. So what we are doing the next time, so we are getting what we are trying to multiply. So let's do this once more. So the next time j would be 1 because incremented by 1. This is going to run till 100. So next time it would be a. So I'm just going to write the values here 0 1. So a 0 1 is equals to b 1 0 into b 2 0, right? So you can see here you are referring A00, A01, A02, A03. All these are elements of a single row. All these are elements of a single row. A00, A01, A02, A03, right? Then later
Sir,
on,
sorry for interruption, sir. Can you explain again that how that two come in A00?
how?
The two value comes in A00.
This one here,
Yeah, this one.
0 0.
Yeah,
It's because I is 0 and J is 0.
I0 and J0.
So we are referring to Aij, na? So A00. Next time A01 because J is going to change. Is this okay?
No, no. I mean that, sir. How did value of two comes, which Iqbal Aziz answer that two?
Okay, that too.
Yeah,
That
yeah,
was a
that
block
two.
size. The block size. I was talking about what is the block size. If what's written over here is direct matter cache with 16 byte blocks. So the block size is 16 bytes. The blocks mentioned over here is 16 byte blocks, and each element is of 8 byte. This means how many elements can come together in a block?
Anyway, two. Okay, fine.
Two blocks, right? So
Okay.
16 byte block. The block size is a 16 byte, but each element is of 8 byte. So this means you can have just two elements,
Yeah,
right?
got
Okay.
it, sir.
Okay. A01, and then the next one would be A02, which would be B20 into B30. Now, once you have done three instructions, you can see some repetition here. So what you're seeing here is there is no repetition in A for this particular case, but for B you can see here that B10 is utilized here as well as here. So at least one element is utilized in the next instruction. So if it's in the cache, that would be the hit the next time. But then you are fetching the new elements. But what are B 0 zeros and 1 zeros and 2 zeros? So when you're talking about B, so B10 is this is B00. This is the first element that was mentioned over here. The first element B00. Then you want to multiply it with B10. Where is B10 here? So B10 is this one. And when you are going to fetch, then you're going to fetch the next row as well. B20 is the next one. B30 is the next one. Okay, so each time you are referring to an element, it's going to be a miss. Okay, so each time you're referring to a new one, it's going to be a miss. So this would be a miss. This would be a miss. But here it would be a hit because you already got that in the in the cache. So this would be a hit, but this would be a miss. Again, this would be a hit and this would be a miss. So if you run this 100 times, if you run this 100 times, how many misses are there going to be for B elements? Anyone? How many misses are going to be there for B elements if you run that 100 times?
Sir, 100. Sir, 101.
101, because in the first one you're going to get 2, but the remaining one you're going to get 1, so that would be 101 misses for B only. Now let's talk about A. A is referred at A00, 01, 02, 03, 04, and so on. So if you check how is A referred, then this is A00, the first element. The second element A01, which is going to be a hit because once you bring in this block, the second one already is there. And then goes for A02, which is going to be a miss, but A03 is going to be a hit. So you're going to see here, if you run all these elements, 100 elements, 50 of them would be miss and 50 of them would be hit, right? So if you come back over here in this particular, so if this is run 100 times, then every next one would be a miss. Okay, so 50 misses for A. Is this okay for all of you? So 101 misses for B and 50 misses for A. Then what happens is you change the value of I, because you have run that 100 times. Now you change the value of I, so I becomes 1 now, right? So if you change I, you can see over here for B there is no I. For B there is no reference with I. So this means that you're referencing the same elements which are already there in the cache. So we are talking about an 8 kilobyte cache, which is now big enough to hold the whole B element together. So this is why we have mentioned the size over here. So this means that when you're going to refer to these elements again, they're already in there in the cache. So the next time you want to refer to B00, that would be a hit. B10, that would be a hit. So all of them are going to be hit because B has already been fetched into the cache. Now we are talking about when we go to the next iteration and I is 1. But here you're going to see that AI was 0, so it changes to A10 and 11 and 12 and so on. Again, the same thing that we did for the first 100 values, that it's going to be a miss for the first one, a hit for the next one, miss for the first one, hit for the next one, right? So again, 50 misses for the second iteration and 0 misses for B, right? So you're going to see here that if you do the same, then in the second one, you're going to see B has got 0 misses and A will have 50 misses again. Then if you go for the third time, when you change the value I to Z2, then again you're going to see B has got 0 misses and A has got 50 misses. So if you calculate, add up all of that, that becomes 150 plus 101. So 150 plus 101 would be, how much would that be? That would be 251, right? So in total, you have got 251 misses for this whole program, right? So in total, it's going to be 251 misses for the whole program. Is this okay? Right? Is this okay now? Now,
Excuse me, sir.
G.
Sir, it's okay, but just one point I want to just clear that. How can you get knows, or how can you know the total size 8 kilobytes that the B will not be uh, flushed from the memory? It will occupy all the
Yeah,
B space.
that's an assumption that we have made, because looking at the size over here, it's 8 kilobyte, which is quite a big cache. If you calculate the number of elements that you want to use, you are fetching just 100 elements over here, right? 100 elements of 8 bytes. That means 800 bytes. So 800 bytes, and your direct map cache is of 8 kilobyte, means that all these 800 bytes can easily come into the cache. That's the assumption that we have made over here. So
Okay, sir.
800
Okay,
bytes
sir. Thank
can
you.
easily come, so you don't have to replace that. Okay, so that's an assumption. Okay, now let's move forward. Now you 251 misses, right? Now let's talk about compiler control prefetching. So if we implement compiler control prefetching and we inserted prefetch instruction before it's needed, just the example I gave you. Now we have now changed the code. The same program is written in a different way. Uh, it's divided into two different loops. This is your first loop, which is having a constant value of I over here. The I is taken to be 0 in this case. But next time I is running from for 1 and 2, right? So 0 is separated where we are going to do the prefetching for B, because B is needed just once, and a prefetching of A is going to be done over here as well as over here. Now the idea is, since the miss penalty is such, so we all always talking about in terms of miss penalty. So the miss penalty is such that it's beneficial to start prefetching 7 iterations in advance, right? Before that, it's not going to be beneficial. So if you are in your 0th iteration and then you are targeting the 7th iteration, then it's going to benefit you. Otherwise, it's not going to benefit you. That's the main idea over here. So when we come to the first iteration, the first thing we do is start fetching the 7th bth element and also the 7th 8th element, because by the time we are going to come to the 7th element, we would already have this value with us, right? So this is going to be beneficial for us. So these are the prefetching instructions that the compiler is going to put in the program. Then it's going to come to the main loop, the main loop instruction, which is to multiply these two elements. Now again, you can see over here now let's talk about the 7 iterations of that loop. So for the 7 iteration, you're going to go in the same way that for each iteration of B, you're going to have 2 misses in the first iteration, then 1 and 1, 1. So this is your 1, 2, 3, 4, 5, 6, 7, right? When you reach your 8th iteration, the bth element that you have tried to fetch in this point is already going to be there. So from this point onwards, all of those elements would be hits. So you are going to experience 8 misses for B, right? For the first 7 iterations, you are going to experience only 8 misses for B. And later on, it would be hit, because in every iteration, what you're doing is you're fetching the 7th element from that point onwards. Okay? So this means by the time you're going to reach that point, it would have been fetched and it's going to be there in the cache. The same goes with A. You are fetching the 7th element of A, but for A we saw that it's going to be hit for 1, miss for first element, hit for next one, miss for first, hit for next one, miss for first, hit for next one, miss for first. So you're going to experience only 4 misses for the 7 iterations, right? So 4 plus 8 means you're just having 12 misses for this loop.
Excuse me, sir.
Reggie,
Will you please explain the message of A again?
misses of A again. So in A, our pattern for A was, if you come back over here, our pattern for A was that for every iteration we were having a miss for the first element, hit for the second element, miss for the first element of that block, and hit for the second element of that block. So in total there were 50 misses for one row, right? Because there were 100 elements, so 50 were misses and 50 were hits. So you are going to do the same thing over here, that the first time you're going to refer to this A element, that would be a miss. But A02, A01, A00 would be a miss, but A01 would be a hit. This would be a hit, so it's not included in the calculations, because this has come when you brought in this block. This is already this has already been fetched. Okay. Okay, so now let's move on to the next iteration, the second and third iteration. So there were 12 hits, but the whole B has now entered into the cache, so there is no more misses for B now. For A, you are going to do the same thing, that prefetching for 7 more. So there you're going to experience 4 and 4 more. So this means for the second one, and for the I is equals to 1 and I is equals to 2, only there would be misses for A. So you are going to add all of these together, 4 plus 4 plus 4 for A and 8. So this would be 12 plus 8 or something like 20 misses in total, right? Um, yeah, 20 misses. So that would be 20 misses. Actually, B plus 7, J plus 7, you have started from J plus 7, J is equals to 0, 7, and that would be here. That's fetched over here. Yeah, that's fetched over here. So this actually is also not going to be there for the 7 iteration because you have already fetched that, started that here. So 20 or 19 misses. It's if you take this, that would be 20. If you don't take this, that would be 19 misses. Compared to the one that we did earlier, that was very large. So you're talking over here in 20 misses, but in the previous one, in the previous slide, we had 251 misses. So this is the advantage. From 251, you have reduced it to just 20 misses because of these prefetching instructions that you have inserted in your code. Okay. So this is the advantage of compiler controlled prefetching, but this advantage is coming at the expense of having more memory bandwidth, utilizing more memory, utilizing more power. Obviously, memory you are fetching more from memory. You are fetching continuously from memory now, right? So the number of misses have reduced. So this is a very good example of how misses can be reduced if you have prefetch instructions in your code. Okay, compiler controlled, and you want to fetch from wherever you want. Okay, so this comes to our last optimization, and this is a summary showing you how every optimization that we have discussed is going to affect the hit time, the bandwidth, the miss penalty, the miss rate, the power consumption, and the complexity, right? So this is for the second topic, the memory topic. You can read these sections together, 2.3, 4, and 6 yourself. This is about the later architectures, the i7s and Cortex A series, how they have. So all of that is whatever optimization that we have done is it's implemented in processor, and it's going to give you the experience of how the processor is going to work. 2.4, 2.3, you're talking about SRAMs and DRAMs. It's for your own knowledge, but it's not part of the course. But if you haven't studied SRAMs and DRAMs, this is a good topic. You can read that yourself. Do as much exercise at the end of chapter 2. So we're not stopping over here because we still have got 20 minutes more, something like that. And so I'm going to start my new topic now. If there are any questions, you can ask me.
Excuse me, sir.
G.
Sir, as we have seen in the hardware prefetching and compiler prefetching, the hardware prefetching was there was a technique that it was prefetching the next upcoming block.
Yeah.
But in the compiler prefetching, we are hard coded the coding that instruction will be prefetched. But what will be the case for the random prefetching? How the compiler will knows that what instruction should I prefetch?
Yeah, this depends on your program. You can control it. You can obviously mention how much how much date elements are needed. So obviously, when you're doing a compiler control prefetching, it's an assumption that the compiler knows somehow about the hardware. Okay, so it knows about the penalties. So it's going to try, if you're working on an array, it's going to try to get elements of array which are at least that much distance away, right? So this is all about compiler knowing about the hardware, and then compilers obviously know about the hardware, otherwise they cannot write or compile the program. So they know about the internal details. So it again also depends on whether that particular processor has got prefetch instructions, because this is again only going to be beneficial if the processors have those kind of instructions that the compiler can use. So this is about if you're talking about randomly getting something from the program, that can also be done, but it's kind of a controlled by programmer. right? So if a programmer cannot control that, then the compiler can do that, but it won't be as beneficial. But still, the compiler knows that if you are going to access some elements, it's going to know how much elements are you are trying to access, for example 100 elements. And if it's beneficial to get an element which is at a location of 7 bytes from this place, or seventh element from this place, because the prefetching is also going to take say that much time, then the compiler can obviously start prefetching from some known location. And this is something that the compilers do these days. So they not only prefetch, they also do different other techniques as well. Not and this is about the compiler. Your operating system does also many prefetchings, and the operating system, since that's not a topic, because we are sticking to memory right now, the operating system tries to prefetch different tasks that are done uh, by the experience of the of the user. So if the user is going to open a particular application, then the operating system is going to train itself, or it's going to learn itself that this application should always be opened whenever the system goes to this particular stage. And all of these are running in the background. All of these things related to the operating system are also running in the background, where it tries to predict your next application that you're going to open, right? And this is for the latest operating systems as well. So there are many things going on regarding optimizations, not only from the processor side, but from the operating system side, from the compiler side, to improve the performance, right? So obviously all of that needs a little thinking of how that could be done, but it's not very difficult. It's not very difficult to think of ways to implement that. Many a times you are going to lose, you're not going to predict correctly, but most of the time if you predict correctly, then it's obviously going to be very beneficial for the overall program and the whole user experience, right? But it also consumes a lot of power. So that's why you're going to see that if you have Windows 10 implemented, with Windows 10 installed, and you are running a laptop without power, then it's going to run much slowly, because if your laptop tries to balance the power consumption, and your operating system is trying to open many different applications, then there is a problem there. Because there is, at one point, there is a power consumption from the hardware level, and from the operating system level it's trying to open more resources. Then a different sometimes the system hangs as well, right? And if you disable the power consumption module that the hardware is controlling, then you're going to see that it's going to run smoothly. So even though your battery is full, but there are different things happening. So power consumption is controlling that. Since the power is not there, it's going to limit the number of operations or number of tasks the operating system can run. But the operating system is trying to predict and opening more instructions or opening more programs. So that is something that happens in today's operating systems and the hardwares that we have, right? So there are different optimizations that are there. So not everything can be covered in this course. And obviously, if you want to take a holistic approach, then you have to learn much of the operating system along with the processor in order to get what are the benefits and what are the real things happening at these times. And because both of them are synced together, so you cannot build an operating system without knowing the hardware. You cannot work on the hardware without knowing that the operating systems are not utilizing this feature. Okay. Right, so our next topic is again going to be ILP. So we are coming back to instruction level parallelism that we discontinued from 3 lectures ago. But this time we are going to talk about the recent architectures. So we are going to talk about how the recent architectures work. So the main target here would be scheduling techniques. So starting with static scheduling, we are going to go to dynamic scheduling, which will be a topic of our next lecture, not today's lecture. But dynamic scheduling is the main thing, how our processor is going to schedule. So up till now, what we have learned was a 5-stage pipeline, which was scheduling instruction one after another. right? And it was completing instruction one after another. And if there was one instruction which was stuck, then all the remaining instructions are going to be stuck as well. If the one instruction is going to be stalled, all the remaining instructions are going to be stalled. But this is not how things work these days. So we have got dynamic scheduling with speculations. We have learned about prediction that would be utilized here as well. But the main thing is you are going to speculate instruction. You're going to run instructions which are just speculative. You don't know whether they are going to be run or they are needed or not. So you're going to bring in those instructions, you're going to run that instruction, but you're not going to store those results. This is the main thing over here. Okay, so before that, we are going to have one more topic, which is a multi-cycle operation in MIPS pipeline. Here we are talking about a multi-cycle MIPS pipeline instead of a 5-stage pipeline. The assumption here is that our execution unit is going to take more stages. It's not just one stage, it's going to take multiple stages according to the clock cycles needed. And this goes with our architecture, because if you're talking about an adder that we had studied in our second lecture, and a floating point adder that we studied in our sixth lecture, we can compare these two adders together. A basic integer adder is a very simple adder, but if you're talking about a floating point adder, it has got many tasks. It's going to unpack, it's going to do the sign additions and shifting according to that. It's going to compare the if it's going to compare the exponents. It's going to shift the significance. It's then going to add the significance. It's going to normalize the result. It's going to change the exponent. It's going to determine the sign, and then pack the whole thing together. So this is a bigger process than a simple single cycle operation. So if you're talking about doing everything in a pipeline, then assuming that an integer floating point operation and a floating point operation both are going to take one cycle, this is not a good assumption. So in a multi-cycle operation, our main point is that we are going to have as many cycles as needed by that operation, right? So a floating point operation are obviously going to take the floating point operations are obviously going to take more than one cycle to complete, right? So we are going to make changes in our pipeline. Our EX stage is going to have many different directions, so you can choose any one of them, and it depends on what particular operation you are selecting, and each of them is going to take a different number of cycles. So this is our diagram here. So you can see here we have the same fetch stage, the decode stage of a 5-stage pipeline, and the last two stages, the memory stage and write backs, are also same, except for the execution stage, which is going to have 4 different paths. So if you have an integer operation, you are just going to take the topmost path. If you have a floating point and integer multiply, it's going to take 7 stages, which are shown over here. These are 7 stages. If you want to take a floating point addition, it's going to take 4 stages. If you want to take division, they are probably, I think so, 17 stages or something like that. So I don't remember that, but this is the main thing here. This is that the execution stage is divided into different paths, and each functional unit is taking different number of stages, from 1 to 4 to 7 to, that was 23 if I remember. Anyway, it is there in the slide. Okay, in terms of latency, then the latency is the number of cycles between an instruction that produces a result and an instruction that uses that result. So if you have got 2 add instructions coming one after another, obviously these 2 instructions are going to have a latency of 0. The second add instruction is not going to wait for the first add to complete, because that is pipeline. So you can have both of these operations going one after another. The main thing here is that these 2 instructions are not using each other's result, right? So the first one is not producing a result and second is not using that result. You're just talking about 2 operations of the same type. So that's the latency. The initiation or repeat interval is the number of cycles that must elapse before showing 2 operations of the given type. So if you have got 2 types of operations together coming after another, so how much time have you got to wait for the second operations of that same type to start. So if you have got an add operation and another add operation, you need a single cycle in between that. So you cannot start the two add operation in the same cycle. You have to start one add operation in one cycle, and after one cycle you can start another add operation. This was about integer. This was about data memory. A floating point add. A floating point add has since got four stages. So the second one has to wait for three cycles. I'm going to come to that if it's not clear. So what I mean here is that if you're talking about a floating point add operation, that is going to take four cycles to complete. Four cycles for the floating point operation, right? So let's say we have got four stages, right? So the last stage is obviously going to produce a result. So if you have got another floating point operation that's coming in, and that's also going to take four stages, that operation can obviously start, because if you have got two add operations where one of them is writing a result to a floating point register F1, and the second add operation is using that in its operations as an operand F1. So it needs to add F1 and F3, right? So it needs the result F1. So obviously that result is not going to come before this particular stage. So next floating point operation can start from the very next cycle, but when it comes to that particular execution state, it's going to see that the operands are not available. So it has to wait for that operation, right? And how many cycles that it has to wait? It has to wait for three cycles, right? Because it's going to start one cycle later. So if the decode stage for that particular instruction was at this point, the decode stage for this add instruction is going to be, sorry, the decode stage for the second add instruction. If so, I'm going to wrap something over here. So if the decode stage for the previous add is here, then the decode stage for this add is going to be here, right? This means that after that it has to wait for 1, 2, and 3 cycles, because then it can start with its execution. Then you can forward the result from here to here, right? So 3 cycles are wasted. That's shown over here in this diagram, in this graph, in this table here, that latency, the number of cycles between an instruction that produces a result and instruction that uses that is a floating point add. If you have got a floating point add producing a result, how many cycles does the next instruction has to wait for to use that result? And that is 3, because that's a 3 stage, and that's 6 over here because that's 7 stage, and 24 over here because that's a 25 stage. So 25 stage for division. So 25 stage for division here. And initiation interval is 1 for all of them except for division, which has got 25 cycles, because you cannot, because this is not pipeline. So if not pipeline, then you have to wait for the second divide operation for 25 cycle to use that divider. That divider is not available till 25 cycles, right? So in other words, what we are trying to say is that addition is pipeline, multiplication is pipeline, but for division, it's divided into 25 cycles, but it's not pipeline. So the whole division process is not pipeline. It's, however, going to take 25 cycles to complete. Okay, so if anyone needs a result, it's going to wait for 24 cycles to get that result, because that decode part is going to come over here, then at 24 cycles wait, and then it can use that result at the end. If there are 2 division operations, so if the first divide is not complete, the second cannot start. So it's not like add or multiply where you can start from the very next cycle, because it's not pipeline. It has to wait for the whole 25 cycles to start new operation. So this was about a brief introduction to the multi-cycle operation in MIPS pipeline. Now, since we don't have much time, I would like you to go through these slides. They are not very difficult since you have gone through the pipelining yourself. Here we are just talking about how this pipeline is going to behave, right? So you have got the idea. So the main idea here is that instructions which are later in order can complete before the previous instruction. So if you have got four instruction, multiply, add, load, and store. So multiply takes a lot of time. Add takes a little less time than that, but it's a later instruction. But you can see here that it's completing before the multiply operation, and load is even completing before the add up. This is an assumption where you are going to see that this is taking into account that all these four instructions are independent of each other. If there was some dependency, then obviously you are going to, so for example, if add was using a result of multiply, then add is obviously going to start its execution stage from this point, right? So we are saying that all these four instructions are independent. So if they are independent, then this means that they can complete earlier in time than other instructions, right? The other thing is that it could happen that say for example, if instead of add at this position, if add was at this position, so add would have started over here and ended at this point. So you would have seen that there are two write backs in the same cycle, again causing a structural hazard, right? So these are difficulties in a multi-cycle operation that we need to discuss. So you can just go through that these slides. Here we are going to talk about the different hazards that are going to come, the write after write hazards, and we have discussed that earlier in the previous slide where we were talking about the raw hazards and the war hazards and the WOV hazards, right? That was about dependency. So when you're talking about raw hazard, that's a read after write hazard. That's the data dependency that we have discussed, and then the WOV hazards are output dependencies, and war hazards are the name dependencies. So this is about the structural hazards. What I was discussing, that they can be different write operation the same cycle. How to make sure that they are different. So there are different techniques for that, and it's all mentioned in the slide. So you just have to go through that. It's not very difficult. What are chances of two instructions writing to the same registers like this? So what can happen when one of them completes earlier, like the load to F2 happens earlier than the add operation. So what value is going to come over here in F2? So what is F2 going to store? So that is something that you can do. And then we are going to start from again static scheduling, something that you can do as yourself. So I'm going to give you this as an exercise to go through that yourself. I'm going to discuss that in the next class about what is static scheduling, how can we do these schedulings, how to do schedule this code. So you can go through these slides. I'm going to come to the dynamic scheduling part in next chapter. So all of that is quite easy. Go through that. I'm going to discuss that in the next class as well. But please go through that yourself. Try to see what did you get from these slides. So I'm going to come till loop unrolling over here, and then this is all type of is included in static scheduling, and then in the next class I'm going to discuss that, and then I'm going to come to dynamic scheduling, which would be my main topic of the next class. Right, so I'm going to stop over here. Again, request for all of you to write your roll numbers in the chat so that I can mark you, and then you can leave. So all of you were there except for one today who was not present today. Who was not here today?
Excuse me, sir.
G.
Sir, in the previous page, you were discussing the adding of floating point number.
Yeah.
The latency of 3. You have given the second instruction that add F1 and F3. Then the second add operation will wait till the result is generated of the F1. So
Yeah.
but if the second instruction is not dependent on the result of the first instruction.
Yeah.
So will it wait till the
No, no,
three
no, no,
cycles?
no. That was the some. That was. Where was that? So actually, that was slide number. Yeah, here. That's your the latency is when you are producing a result and the second one is using that. And if they are independent, right? If they are independent, then obviously they don't have to wait for each other. Because they are independent, they can start from the very next cycle. The initiation interval is if you have got two operations of the same type, how much is the second operation going to wait? So this means that you cannot start two floating point adds at the same time, at the same cycle. There is an initiation interval of one cycle, which means that two add operations should have a difference of one cycle in between them. Okay. So if you have got two add operations, you cannot start both of these add operations the same cycle. Now this is because you're going to see here that because this is a multi-cycle operation, you're going to see that many writes are going to happen in the same cycle. Reads can happen in the same cycle as well, right? So they can be different orders here. So what initiation interval is going to tell us is that if, for example, you come across a sequence where you can start two floating point adds together, then this cannot happen because you need a single cycle in between two floating point adds, right? This is if you have got an add instruction and an add instruction in the execution state, both of them cannot happen at the same time. You need at least one cycle, and this is normal in pipeline. You have got a single cycle in between two different operations.
Okay, sir. The one cycle is mandatory, but the three cycles latency is
Three
dependent
cycle
on the
is
result.
Yeah, three cycle is about if you have got two operations where you are producing a result in the first one. So if this is an add floating point add which is producing a result, and say a floating point multiply is using that result. So the question is how much time is the floating point multiplier going to wait? So because add has got four stages, the result is going to come at the end of this cycle. So multiplier can only start its operation from this cycle. Now, because that before that it was decode stage. So decode stage of floating point multiplier is obviously going to start from here because this is issued a cycle later than add. So this means that these three cycles are going to be wasted.
Okay, sir. Thank you so much. Now
Right?
it's clear.
Okay.
Thank you, sir.
Okay, so since everyone has written their roll number, now you people can leave. Our next class will be inshallah next Thursday. And for the time being, it has been decided that all of these classes are going to be online for this semester at least. I'm not sure about the examination, the final examination, but for the time being, the classes are online.
Okay, sir. Inshallah.
Okay.
Allah Hafiz, sir.
Allah Hafiz.
Allah Hafiz, sir.
Allah Hafiz.